Okay. Okay, so what I'll do is I'll go over this third isomorphism theorem once again so that those who are going to see it, which is about less than 10 people, about 7 people, but anyway, let's just go over it. Yeah, so, and anyway, it's a good idea to go over things again and again. Yeah, so so first and second isomorphism theorem we discussed last time. And the third isomorphism theorem says that so R is a commutative ring with unity, I and J are ideals of R, and I is contained in J. Then R mod J is isomorphic to R mod I, mod J mod I. Yeah. So this is a J mod I is an ideal of R mod I. So the right hand side here makes sense. Yeah. So this we saw last time when we were studying quotients of rings. Quotient rings by ideals. Yeah? So relating ideals in R mod I with ideals in R. So J mod I is indeed an ideal in R mod I. And to prove this, what we'll do is give a surjective ring homomorphism from R mod I to R mod J. And the ring homomorphism is A plus I goes to A plus J. So we check that this map is well defined. So this is like group theory. Yeah. So you think of this guy. You think of R mod I plus as a group and R plus as a group, and I don't know I mod J plus as a group, and apply your group theory result here. A billion groups, in fact. So phi is well defined because you are taking a further quotient. So A plus I is same as A prime plus I, and A minus A prime belongs to I implies it's can belong to J because I is contained in J, which implies A plus J equals A prime plus J. And then you'd see that it behaves well with respect to multiplication. So phi of A plus I dot A prime plus I is same as phi A prime plus I by definition of multiplication, which is same as A prime plus J, which is same as A plus J times A prime plus J, which is which by definition of phi is phi of A plus I times phi of A prime plus I. Yeah? And phi is surjective is clear. The image of A plus J is just A plus I for any element A of R. So phi is a surjective ring homomorphism. Now we look at the kernel. So kernel of phi, the claim is kernel of phi is equal to J mod I. So A plus I belongs to kernel of phi if and only if phi of A plus I is 0 in R mod J. And phi of A plus I is same as A plus J, and that is 0 in R mod J is equivalent to saying that A belongs to J, which is equivalent to saying A plus I belongs to J mod I. So now by first isomorphism theorem, we have that R mod I mod the kernel, which is J mod I, is isomorphic to R mod J. Okay, so this is the third isomorphism theorem. So let's get to this example again. So I wanted this notation. Yeah. So if you have some elements of the ring R, for instance, 2 elements here, then the ideal AB generating R or whatever number of elements, it may be 1 or maybe 10, is also denoted by this round bracket around this guy, around these elements. Yeah, and from the context, it will be clear which ring, to which ring this ideal belongs. So if there are many rings floating around and these elements are there in all these rings, then from the context it will be clear. Like in this example, so Zx, so n belongs to Zx as well as Z, and in the left hand side this ideal is n times Gx, and on the right hand side this ideal is n times Z. Okay. So to show that these two rings are isomorphic, we'll use the first isomorphism theorem. So we define ring map, ring homomorphism from Zx to Z mod n Zx, where f goes to f mod n. Yeah. So this means that, so say f is this polynomial en x power n plus En, sorry, no summation if I'm writing it this way. So En minus 1 x power n minus 1 dot a0. Then it goes to, so maybe I'll put m because n is taken there, yeah. So this is the n. So let's just say our polynomial will look like this, yeah, a typical polynomial. So its image here is f mod n. What I'm trying to say is what is f mod n, yeah. So you look at am and its conjugacy class in a mod n, yeah. So this is sometimes the notation used. So and then nothing, do nothing to the variable, yeah. So s plus am minus 1 class of am minus 1 in z mod nz x power m minus 1 plus class of a0 in z mod nz. Yeah. So this is the ring homomorphism. And of course, this is surjective, right? Because, I mean, given any polynomial, you can lift it. So this is well-defined map and it is surjective. And then one has to check that this is a ring homomorphism. So this is also not, I mean, this is same amount of check as z goes to z mod nc is a ring homomorphism. Yeah? So phi of f plus g is by definition f plus g mod n. So f plus g is a polynomial and you go each coefficient mod n, but this is same as first taking mod n of each coefficient of f, and then I'm taking mod n of each coefficient of g, and then adding them. Yeah, so the answers will be same. Yeah. So I have brought in the second example right away. So okay, so maybe I'll erase it. Yeah, it will have to go a little down. Okay, so this tells us that this is same as phi of f plus phi of g. And similarly, you can check for multiplication. So similarly, phi of fg is phi of f. So this is same as saying first going mod n and then multiplying the two polynomial is same as first first multiplying the two polynomials and then going mod n. Yeah. Okay. So so phi is indeed a ring homomorphism. So from this we get that phi is ring homomorphism, and of course it is surjective, and surjective is clear. Right? So that's the tautology. And what is the kernel of phi? So the main step is to just calculate kernel of phi. So kernel of phi is those polynomials f in Zx such that f mod n. So we'll just explicitly calculate this. Yeah, f mod n is the zero polynomial in z mod n cx. Yeah, so since I'm using this, I'm not using class or something, bar or something. So let's just say zero in this this ring, z mod ncx. So this means that each coefficient of f is divisible by n. Yeah, this is the map. So that tells you that each coefficient, so zero polynomial means all the coefficients must be zero. So this is same as saying each coefficient of f is divisible by n, means f is f belongs to nzx. Yeah, this is same as saying f belongs to zx such that n divides n divides fx. Each coefficient of f is divisible by n, so in particular n divides fx, which is same as n zx. So by first isomorphism theorem, we have that zx mod n zx is zx mod this kernel n zx is isomorphic to z mod n zx. So zx mod this kernel is isomorphic to the polynomial ring in one variable over z mod n c. Okay, any questions about this example? Okay, so instead of going through example 2, I'll directly jump to example 3. So example 2 was discussed towards the end of last lecture, so you can read the notes from there. And this is actually similar to example 2. So it's okay. You won't lose much. So let's look at this example. So of course, here we will use the third isomorphism theorem. So there are some ideals one has to worry about. So we'll take I to be 5 zx. Okay, and j to be, j was the bigger ideal, I hope. Yeah, j was the bigger ideal. So j is 5x square minus 2 times cx. Yeah. So this is our setup, and we try to apply our third isomorphism theorem. So what does the third isomorphism theorem says? It says that R mod, and R is of course zx. Yeah. So by third isomorphism theorem, R mod j is isomorphic to R mod I modulo j mod I. Yeah. So R mod j here is the left hand side. So this is zx mod 5 comma x square minus 2. And what is the right hand? So let's just decode this part. So R mod I is zx mod 5zx. Yeah. And modulo this j mod I. Yeah. So j mod I is yeah. Okay, it's okay. So j mod I is the ideal generated by 5 comma x square minus 2 mod zx mod 5 zx. Yeah, so let me just write it in full, the definition. Yeah, but in the previous problem we saw that zx mod n zx is isomorphic to z mod n zx. Yeah, and we know what the map is. In fact, a class of the polynomial goes to that class. Yeah. So this guy, the numerator is same as z mod is isomorphic. So maybe isomorphic to z mod 5z x. And what happens to below? So one should look at under this isomorphism, where will this ideal go to? Yeah, this quotient ideal will go to. So you just have to evaluate mod n. Yeah, that is the map phi, or the induced map phi bar. So one has to look at where under this map. So under mod 5, what will this ideal be? So under mod 5, this ideal will become, so 5 will become 0. So this is just going to be x square minus the class of 2 in Z mod 5. Yeah. So which also we denoted by 2 bar. Yeah. So let me just use 2 bar. Or let me just edit here. Yeah. So let me just call this. Sorry. Just so that it's clear. Yeah. So this is what it means. So a class of 2 in Z mod 5. Yeah. So the image of this ideal in Z mod 5x of this ideal in Z mod 5x under this this isomorphism is precisely x square minus 2 5 Z mod yeah, sorry. Times Z mod. So I mean, as I said, we will use this notation as well, but let me just shift it for next time. So we get this. So this is by definition, this is same as Z mod 5Z x mod x square minus class of 2 5. Yeah. So in the other example, this 5 was changed to 2. So if this 5 were 2, then this will be 0 element, but because the class of 2 in Z mod 2 is 0. Yeah, and that's why we got that answer. But in general, for n equals 5, you get this. So this is some other ring, and in fact, you can show that this is actually. So we will see that sometime later that this is actually an integral domain. So the other ring, when n is 2, this is some polynomial ring mod x square. So this is not even reduced. Yeah, x is nilpotent. Square x is non-zero, but x square is 0. But so note that. So let me just, since I'm talking about it, let me just say what I was discussing. So Z mod x2 mod x square minus 2. This similarly is isomorphic to Z mod 2 Zx mod x square. And so this right-hand side ring is not reduced because x is non-zero, but square lies in the ideal below. So a square's class of the square is actually 0. So it has a non-zero nilpotent and hence is not reduced. Not reduced. But this guy is we will see actually is an integral domain. Okay. Later. So that requires some checking, but we'll do that later. So as you can see, if you change n, this can become so it can become non-reduced. If you take some other value of n, it can become integral domain. Of course, if you choose n properly, it could also become a ring which is not an integral domain, but it is reduced. So you can get all three possibilities. Okay. Any questions on this example? Okay, so if there are no questions, let me move on. Okay. Okay. Yeah, so the bottom line will be visible soon. Okay. Okay, so now we'll talk about prime ideals and maximal ideals. So let's start with prime ideals. So by the way, these isomorphism theorems are sort of building blocks. So I mean, later on, people sometimes even, I mean, at least in the papers, etc., not in the homework problems, people don't even bother saying isomorphism theorem. This is triviality. In some sense, if you work with it enough, then this will seem like a triviality. So you would be able to see these are isomorphic without much of an issue. Okay, so let's get to this prime ideals. So let R be a commutative ring with unity. An ideal P of R is is said to be a prime ideal if so first condition is it has to be a proper ideal. You don't allow the whole ring, and you shouldn't consider the whole ring as prime ideal. So first criteria is it has to be a proper ideal, and A times B belongs to P for some ABA in R, then A belongs to P or B belongs to P. Okay. So it's sort of motivated from, so I'll go over this example of integers, and you'll see that this is sort of motivated from prime numbers in Z. Yeah, so definition of prime numbers in Z. So it's precisely the definition of prime numbers in Z in some sense, except for a minor thing. So in Z, for instance, the prime ideals, so n times Z is prime ideal if and only if n is prime number or n equals 0 is a prime number. So maybe I should have made it a little smaller. Now you can see most of the left. Okay, so if and only if n is a prime number or n equals 0. So that means if you take n equals 0, that is the 0 ideal. Yeah. So the prime ideals in NZ are precisely P times Z, where P is a prime number, and or the 0 ideals. So these are the only prime ideals in NZ. That's what this example says. Okay, so let's just check. So 0 is the prime ideal. Yeah.
So shouldn't n equal to 1 also work?
If you take n equals 1, what do you get?
Z, the whole of Z.
But our definition of prime ideal says it has to be a proper ideal. Yeah. So P is not allowed to be whole of R.
Okay.
Yeah. So we don't allow 1 to be a prime number. Okay. Prime ideal. So whole ring is not allowed to be a prime ideal by definition. Any other questions? Okay, good. So let's just check that 0 is the 0 ideal is indeed a prime ideal. So we'll check that 0 and PZs are prime ideal, and then we'll do the other direction as well. Yeah. So 0 is a prime ideal means that if so to check that, we have to check this definition. So it's of course a proper ideal. You have to check that A times B is 0. Then of course either A is 0 or B is 0. Yeah. So 0 is a prime ideal means we have to check that A times B belongs to 0. So if it belongs to 0, it has to be equal to 0. Yeah, there is only one element in that ideal. So that, but for integers, we know that A times B equals 0, then A equals 0 or B equals 0. And hence, that means A belongs to the 0 ideal or B belongs to the 0 ideal. So this definition is true. So it is a prime ideal. And of course, you can replace Z by any integral domain. Yeah, so that is the note I put. So I should have delayed it a little further. But so in fact, what you can say is, so you come to this remark. So this maybe I should have written it on this spot. So this proof shows that if R is an integral domain, implies 0 is a prime ideal of R. So this argument, and in fact the converse is also true. So if 0 is a prime ideal of R, so I mean this is sort of equivalent. 0 is a prime ideal of R. That means if A times B is equal to 0, then A has to be equal to 0 or B equals 0, which is same as saying that R is an integral. Yeah. So R is an integral domain. For R, a commutative ring with unity, R is an integral domain if and only if the 0 ideal is prime. Okay. So this first statement, the same proof works. Now for n not equal to 0, say n is a prime number, n a prime, let AB belongs to NZ. Yeah. So what does that this statement mean? This means that n divides AB. Yeah. AB is a multiple of n. And if n is a prime number, then you say we'll get that n divides a or n divides b. That's the definition of prime number in integers. Yeah. And if n divides, so n divides a is equivalent to saying that a belongs to n times g, and n divides b is equivalent to saying b belongs to n times c. So this statement, so I guess this is equivalent. Yeah, a belongs to nz or b belongs to nz. So if n is a prime number, then we see that n times z. So this tells us that n times z is a prime ideal. So this tells us nz is a prime ideal. Is a prime ideal. Okay. And maybe I shouldn't use green. Let's use red. It's more visible. Okay. And then if n times z is a prime ideal, let n divide. So now we want to show that n is a prime number. Yeah. So let n divides ab. Then we want to show that n divides a or n divides b. So n divides ab means ab belongs to nz, but nz is a prime ideal. So that tells you that a. So this is where we are using nz is a prime ideal. So a belongs to nz or b belongs to nz, which is equivalent to saying that n divides a or b, n divides b. Yeah, which implies, so this collectively implies n is prime. Okay, so prime ideals in Z are precisely this. So that is the motivation for prime ideals for the name prime ideals. Okay. Any questions? Okay, so if there are no questions, let's take a 5 minutes break. So maybe 8 minutes break. So we'll resume at 12:05. Okay. So let me pause the recording. Okay. So let's resume. So are there any questions? Okay. Okay. So maybe I'll start. So I would like to do more examples, but unfortunately, one needs to decide something as a prime ideal in a slightly more complicated ring is a little bit of work, and which involves some theorems, etc. So we'll have to do a little bit more theory to see more examples and so on. But some examples we'll still see. But let me do a little bit more theory, and then maybe on Google Classroom I'll post some examples and people can discuss. So maybe that will be more fun as well. Okay. So so now I'll start writing on this spot so that everyone is happy. Yeah. So we made this observation that R is an integral of domain if and only if 0 is a prime ideal of R. So in fact, a decorated version of this this thing is maybe this proposition. So proposition. Let R be a commutative ring with unity, and this and I contained in R be an ideal, then so maybe then the ring R mod I is an integral domain domain if and only if I is a prime ideal. Okay. So recall in the definition of integral domain, we assume that the ring is it's a commutative ring with unity and is non-zero. Yeah. So that all. So R mod I is an integral domain. In particular, means that I is not the whole ring R. Yeah. So let's see a proof of this guy in this statement. Yeah, so it's like, as I said, it's a sort of a decorated version of the previous statement. So, so the proof will also be one line. So note that R mod I is 0 if and only if I is equal to R. So R mod I is an integral domain, in particular, if and only if I is a proper ideal of R. So not it should be a proper ideal, yeah. So for R mod I to be an integral. Okay. So maybe I'll start from left hand side, yeah. So R mod I is an integral domain if and only if I is not equal to R. So it should be a non-zero ring, a non-zero commutative ring with unity. So commutative ring with unity is guaranteed because R is, and it's a non-zero ring because I is not equal to R. And we want every non-zero element should be a non-zero divisor. Yeah. So this one can say it this way. So A bar. So I'll write it this way. So and A. So I'll use, instead of writing A plus I, I'll use A bar and B bar notation. Or maybe alpha, let's just use alpha beta, alpha and alpha beta in R, and for alpha beta in R mod I, alpha times beta equals 0 implies alpha equals 0 or beta equals 0. So this is the definition of integral domain. Yeah. And then this statement is equivalent to saying that I is a proper ideal of R. I is not equal to R. And so alpha beta are elements of AB. That means alpha is, let's say, A bar, and beta is B bar for some AB in R, and A bar B bar, sorry. So we are given that A bar B bar is equal to 0 implies A bar equals 0 or B bar equals 0 in R mod I. Yeah. So these are all elements of R mod I. So it should be 0 in R mod I. So what does it mean to say A bar B bar is 0 in R mod I? So A bar B bar is same as AB. Yeah. So this is equivalent to, let me get here. So this is equivalent to saying I is a proper ideal of R, and for AB in R, A bar B bar, AB bar is 0 in R mod I is, yeah, so maybe I'll not make, I mean, I'll not elongate the statement further. So this is same as AB bar. Yeah. So AB bar is 0 in R mod I. That tells that this is equivalent to saying that AB belongs to I. Yeah. Implies A bar is 0 in R mod I means A belongs to I or B belongs to I. Okay. So so what do we get? We get that so this is precisely the definition of I is a prime ideal. Prime ideal of R. Okay, so as you can see, it's the length of the proof is more. I mean, though one has to write more words, but I mean, it's exactly the same proof as the previous line. So the ideas involved is exactly the same. Yeah. So this is one way to check whether some ideal in the ring R. It's frozen. Yeah. This is one way to check whether an ideal in a ring R is a prime ideal or not. You go mod that ideal and check whether it's an integral domain. Okay. So as an application, maybe I can do one example here. Yeah. So as an application, yeah. PZX is a prime ideal of ZX if P is a prime number, is a prime. Yeah, because because we saw that since we saw that ZX mod PZX is in fact isomorphic to Z mod PX. Yeah. And we know that Z mod PZ, this is a field, and polynomial ring over a field. In fact, polynomial ring over an integral domain is an integral domain. Yeah. So this is a field and hence an integral domain. So the polynomial ring over this is also an integral domain. So since this is an integral domain, the corresponding ideal must be a prime ideal. Okay, so this is integral domain. Okay, so this is one example. Another example, maybe, yeah, so Q, this also we sort of saw, but there's this remainders theorem which comes in x square minus 2. Yeah, so we saw that this is isomorphic to Q square root 2. The smallest ring, subring of R containing Q and square root 2. Yeah, so that tells you that so this implies, this isomorphism implies that the ideal generated by x square minus 2 in Qx is a prime ideal. Because the right hand side is a subring of R, yeah. So it has, I mean, it's actually, so one can also show that this is actually a field, but that's a different point. But at least it's an integral domain, yeah. So it's a subring of R containing Q and square root 2. So a subring of an integral domain is an integral domain. So, okay, any questions? Okay, so if there are no questions, so we'll see more examples. Yeah. So in fact, yeah.
In the first one, 0 will also work.
Yeah. So even 0. So there are many more prime ideals in ZX. Yeah. So 0 is also a prime ideal because ZX is an integral domain. Yeah. So another class of examples you can get is in ZX. So this I won't work out, but maybe I'll put it on Google Classroom. Yeah, so you can show that. So you can show that, for instance, x minus 5 or x minus any integer n, the ideal generated by x minus n is a prime ideal for n any integer. Yeah.
Ideal of a integral domain are always prime ideals.
No, that is not true. So maybe, yeah, so one example like that, yeah. So in fact, we know that Z is an integral domain, yeah. And we saw that the only ideals which are prime ideals are generated by the prime numbers. So for instance, 6Z is not a prime ideal of Z, yeah. Or 4Z is not a prime ideal of Z. And even in the polynomial ring, if you take something like x square minus 4 in ZX or in QX, so those things won't be a prime ideal. Okay. So somehow that's so this is going to be a prime ideal. In fact, if you think about x square minus 2 in ZX, the ideal generated by x square minus 2 in ZX, that is also a prime ideal. Okay. So these are these are various examples of prime ideals. So I'll put this 3 on Google Classroom. So it won't be a homework or an exercise. It will be some things one can just do and discuss. Yeah. So and maybe more open-ended questions, some prime ideals of certain things. Yeah. So one can analyze and discuss. So that it's I think it's more fun to discuss things. Okay, so this is some things about prime ideals. So there is another class of ideals which is important. Okay, which are also examples of which are also special cases of prime ideals, but they are called maximal. So they are slightly different. They are better than prime ideals. They are maximal ideals. Okay. So we'll show that maximal ideals are prime ideals, but from definition it won't be evident. Yeah. So so now I'm defining maximal ideals. So. Okay, maybe I'll write the darker. Definition. Maximal ideals. So as I said, many of these definitions can go through even for non-commutative. So maximal ideals certainly. Prime ideals I have mostly seen in commutative ring theory. Yeah. So I haven't seen prime ideals much in non-commutative ring theory, but I haven't looked at non-commutative ring theory much. Yeah. But maximal ideals you can see it in non-commutative ring theory as well, but we won't worry about it. Yeah. So we'll always assume our rings are commutative rings with unity. So let R be a commutative ring. R be a commutative ring with with unity. An ideal M of R is called a maximal ideal of R if it is maximal in some sense. So see, the point is the whole ring is an ideal. Yeah. So if you drop that and that ideal, then it's maximal among proper ideals. Yeah, it's called a maximal ideal if M is maximal. So I'll put it in words first. Maximal among proper ideals of R. And that's why the name maximal ideal. Okay, so why is it writing so funny? Okay. Yeah. So if that if there is some ideal I contains M is contained in R, I an ideal, then we have either M equals I, so rather M is fixed, yeah, so let's write it in a more reasonable way. Then I equals M or I equals R. Yeah. So you can't fit in another ideal between M and R. That is what it a different ideal between M. It's strictly between M and R. That is what this means. Okay, any questions? Okay, so we will see, maybe next time we will see that every commutative ring with unity contains a maximal ideal. Yeah, so this is something which we'll see next time, that R be non-zero. So here we need non-zero ring. So ring, non-zero commutative ring with identity. Commutative. If R is the zero ring, of course, there can't be any maximal ideal. Any proper subset is empty. Yeah. So let R be a commutative, a non-zero commutative ring with unity. Then R contains a maximal ideal. So there exists a maximal ideal for R. Yeah, I don't know, whatever way you want to phrase it. So this uses axiom of choice. So it uses Zorn's lemma because we are not assuming anything about R. Yeah, but so since this uses Zorn's lemma, I don't want to start it towards the end of the section class. But let's see some examples. Yeah, and then we will see that it's very close to. So it is. So we'll also see that maximal ideals are prime ideals in a bit. But let's just see some examples. At least we will verify that in some examples we have seen. So in Z, yeah. So of course, zero ideal is not going to be maximal ideal in Z. Right, because pretty much any ideal nz n not equal to 1 will be an ideal which will be in between zero ideal and R. Yeah. So zero ideal is not, but what about PZ? So other prime ideals. So let P be a prime number. Then PZ is a maximal ideal of Z. So why is that? So you just check whether it satisfies this guy or not. Yeah. So so here, so there are two definitions of primes in in integer. One definition is this one. If P divides AB, then P divides A or P divides B. This is one definition of prime. The other definition is P is a prime if it has only two factors, 1 and P. Yeah. And for integers, these two are we know that these two are equivalent. So there are two ways of thinking about prime numbers, so to speak. Okay. So for this one, we will use the second one, a second definition. That is, the only factors of P are 1 and P. Yeah. So suppose I is some ideal between Z and PZ. Yeah. So I is some ideal between PZ and Z. Yeah. Then of course or maybe I'll use something else. I don't know. So suppose I contain something which is different. So what we have to show is if I is not equal to PZ, then it has to be Z. So that N belongs to I minus PZ. So suppose I is not equal to PZ, then we want to show that I is equal to Z. And what does that mean? That means N is co-prime to P. Yeah, because N is not a multiple of P, and that means N has to be co-prime to P, since the only factors of P are 1 and P. Yeah, this is where we are using the other fact I was telling you about prime, 1 and P. So then now if the GCD of N comma P is 1, what does that mean? So this we know from about integers, that if the GCD is 1, that there exist AB integers such that A N plus B P is equal to 1. Yeah. Right. So this tells us that 1 we can write it as some Z linear combination of N and P. Yeah. So but N belongs to the ideal I, and P also belongs to the ideal I. Right. And we are assuming belongs to I, and PZ the whole ideal PZ is contained in I. So that tells you that this belongs to I. 1 belongs to I, which implies I is equal to Z. Yeah. So if 1 belongs, then everything belongs. Okay. So that tells you that hence PZ. So we assume that I is different from PZ, then we showed that I is equal to Z. So hence PZ is a prime ideal, is a maximal ideal. Okay, so PZ, so all this ideal PZ, where P is a prime number, is indeed a maximal ideal, and these are all the maximal ideals. Yeah, so there is no other maximal ideal, because of course zero ideal is not a maximal ideal, and if N is not a prime, then NZ is not maximal. So this is also clear. Why? Because so then you can write N as P times Q, where P is let's say P is not equal. P and Q are different from 1 and minus 1. Yeah, or maybe I'll write it differently. Absolute value of P and absolute value of Q are strictly greater than 1. So N could be negative here. But anyway, minus N and N give rise to the same ideal. So if N is not a prime, then N equals P times Q, and that tells you that NZ is going to be contained in PZ, yeah, and also in QZ. But that is enough, yeah. So PZ, which is a proper ideal in Z. Hence, NZ is not maximal. Okay, so every prime ideal of Z, so every maximal ideal of Z is prime ideal, and every prime ideal other than 0 of Z is actually maximal ideal. Yeah, so every non-zero prime ideal of Z happens to be maximal. So this is what this observation tells us. Okay, any questions before we close down? So this is all I have to say today. So we'll end now. So there are some chat. Let me just see. Okay. In the second isomorphism theorem, why can't we use just S mod I instead of S plus I mod I? So someone already answered. I might not be in S. Yeah. So that's why we sort of throw away I inside it. So we consider the subring generated by S and I. Class is not being recorded. Okay. Like partial ordering. What is this like partial ordering? Yeah, so it's so it's maximal under inclusion. Yeah, and inclusion is the partial ordering. So I think that's what Shubhankar was trying to say. Now, are maximal ideal always prime? So yes, this is something which we will show maybe in next class. Yeah. Yeah, so so we will worry only about rings with unity. Yeah, in this class, so this whatever this example with Siddharth was suggesting will work in this case. But we are only consider. So I mean, people don't think about prime ideals and maximal ideals in rings which don't have unity. Okay, so we'll only want to consider rings with unity. Okay. Are there any other questions? Okay, good. So if there are no questions, then that's it for today, and I'll see you guys on Thursday next. Okay, and this so I'll email you about it as well. So maybe this Friday I'll have a short quiz. So I plan to have certain number of quizzes. So maybe this Friday I'll have a short quiz for you guys. Okay, see you then on Thursday. Bye bye.